Okay. So once again, thanks for joining this webinar, the seventh webinar of the series, Technical Talks of CTSoc. I'm going to share my screen for a quick introduction. So let me introduce myself. I'm Fabrizio Lamberti. I'm the Vice President of Technical Activities of the IEEE Consumer Technology Society. And I'm responsible for this area, which is named Technical Activities. It's a new area that has been created 3 years ago in order to align CTSoc to many other societies of IEEE. So the idea of this area is to manage the areas that establish connections between the other areas of CTSoc and the technical society as consumer technology society in general. And it is organized in committees. There are 15 technical committees which have been established since January 2021. And these areas, these technical committees basically cover most of the areas of interest, if not all the areas of interest of CTSoc. And today, two of these committees, the HMI, the Human Machine Interaction and User Experience Technical Committee, and the Quantum in Consumer Technology, QCT, agreed and volunteered to help in the organization of these talks. The technical activities areas is organized, as I said, in these 15 technical committees plus a future directions committee. And within this area, there is a board, the technical committee board, which is chaired by myself and is participated by CTSoc President, Professor Wen-Chung Kao, VP Conferences, Nabuo Kunabiki, VP Publications, Fabrice Labo, who is also President-elect for next year, and VP Industry and Standard Activity, Rahed Abdullah, together with the officers of the 15 technical committees, their chairs, their vice chairs, and secretaries. Each technical committee has its own website. You can access this information, as you know, many of you know, through the main website of CTSoc, going onto the technical activities tab, and then choosing the technical committees. Each committee has its own page with its mission and objective, its officers, members, etc. And these are the officers for the 2023-2024 term. And by the way, please remember that this year there will be the election for next year. So in case you want to candidate yourself, nominate yourself, please get in touch with the officers of the technical committees. The technical committees have been established with a given set of members, but this membership is growing over the time through your network of contacts. Those interested in joining can fill in this application form, which is accessible again through the main page of the technical activities areas on CTSoc website. There is a tab which is a membership application form, and be aware of the fact that you don't need to be an IEEE member at present to be a member of our technical committee. So you can exploit the opportunities offered by the technical committees even if you're not a member of IEEE. The size of the technical committees is not homogeneous. As you can see, there are larger and smaller TC, but each of them is contributing to the growth of CTSoc, supporting the society's activities in the areas of conferences, publications, standards, education, and history. So the technical committees are supporting the development of new applications, are supporting the exploration of new areas of interest for CTSoc. They are supporting the cross-cutting and inter-organization initiatives within IEEE, but also with other organizations as well. And they design and define new areas of technology that could be of interest for CTSoc. The technical committees have many practical roles, and just to give you some examples regarding conferences, the technical committees participate in the definition of the call for papers, contribute reviewers, provide publicity, collect nominations of those members that are willing to serve in technical positions like TPC chairs, workshop chair, tutorial chair, publication chair, TPC members. They provide track and session chair, and they also collect proposals for the hosting of new conferences, and also proposal of academic and industry conference speakers. So being a member of the technical committees offers open a number of opportunities. And here you have some examples. I talked about conferences. We are collecting technical position in conferences like ICC Las Vegas, ICC Berlin, Gaming, Entertainment, Media Conference. We collected positions for associate editors in our journals, IEEE Transaction in Consumer Electronics and Consumer Electronic Magazine. We supported the launch of special sections and issues in journals, special sessions and conferences. We participated to the creation of initiatives with other societies and organizing units like the IEEE Digital Privacy Initiative or the IEEE Digital Reality, collaboration with other society, special interest groups, and the technical talks as well. Just to mention a couple of opportunities open or that have been developed with the contribution of our technical committees. The conference GEM, Gaming, Entertainment, and Media, has been launched this year with the great support of our technical committees. 39 people have been involved in the organization, and we received already 3 times the number of papers that have been submitted to last year editions. And so the conference will be held in Turin next June. So I'm talking about that because of the success of the conference, expected success, as well as because I will be chairing this conference and it is currently open for submission. So if you are working in these areas, please, and of course here we are people from the HMI TC, but also Quantum. So please be consider submitting. The call for paper is open till March 22nd. But I've been asked to advertise also these other call for papers and conferences open for submissions, like the IEEE International Symposium on Consumer Technology that this year will be held in Bali, Indonesia in August. The International Conference on Consumer Electronic Asia, ICC Asia, which will be held in Vietnam, Da Nang, November. And the flagship conference in Las Vegas, ICC 2025, which will be held in January next year. So here you have the call for paper, but please go on the website and check for call for papers, but also please note that we will soon open call for volunteers willing to help in the technical positions of these conferences. Yesterday, we had the TC board meeting, and our editor-in-chief of Consumer Electronic Magazine also reminded us that in order to present or propose a special issue on Consumer Electronic Magazine, there is a policy that says that there's need to be a contribution of the technical committees. And here you see the special issues that are currently open for submissions on Consumer Electronic Magazine, and you can see those with the highlights in yellow are those in which there has been a contribution of the technical committee. So as you can see, being a member of the technical committees is can open many opportunities. So I invite you to join if you have not, if you're not a member yet. Just a couple of words about the new initiative that is being launched, which is the Digital Reality Technical Community. It was born as a digital reality initiative, and then last year there has been a process for transitioning it into a technical community under the lead of Consumer Technology Society, but with the participation of many different societies and council and organizing unit the Reliability Society, the Electronic Packaging Society, the Engineering and Medicine and Biology Society, the Council on Radio Frequency Identification, and the IEEE Standard Association. There are discussions in progress with other societies. So also in this initiative, contributions will be seeked. So again, we will look to the 15 technical committees to get support. And the topics are indeed related to what our technical committees are actually doing. So please, in case you're interested, please let me know. Welcome again to the seventh webinar or talk of this series. The next one will be in March, organized by the MDT-MCSH Technical Committee. Today, the talk has been organized with the support, as I said, of the HMI, Human-Machine Interaction and User Experience, TC, and the Quantum in Consumer Technology, TC. So I leave the floor to the officers of the TC for presenting the speakers. Maybe just with a brief bio. And then, of course, I thank again Professor Vivek Kant and Professor Alex James for giving us their availability to talk today. I leave the floor to Davide, or who wants.
Thank you. So thank you, Fabrizio. My name is David Murphy. I'm chair of the HMI Technical Committee. And it's with great pleasure that I introduce Professor Vivek Kant, who is a very active member of our technical committee and is indeed a very passionate proponent of human-centric computing. And it's one of our goals in the technical committee to raise awareness amongst the CTSoc and amongst the wider IEEE to place a greater emphasis on the human side of what we do. And so Professor Vivek is a professor at the Indian Institute of Technology in Kanpur in India. And he's going to give us a presentation titled Challenges of HMI Design in Complex Socio-Technical Systems. So I'll hand you over to Professor Vivek.
Thank you, David. And please, the floor is yours, Professor Kant. We can see your screen. We cannot hear you anymore, Vivek. No, it was working. Maybe you can check Zoom whether the input is on the top left, in the bottom left. You should be able to see on the arrow pointing up.
Can you hear me now?
Now, yes, perfect. Thank you.
Okay, I'm so sorry about all this mess. Sometimes some of the other tech. Idea is that that we use this opportunity to go ahead and show some of the human-centered dimension of operator experience. And I'll be presenting some of my work over here. So I'll just very quickly share my screen. So a lot of the work that I do is on human factors in complex socio-technical systems. My background is human factors engineering. My PhD work is in systems design engineering with a core emphasis on cognitive human factors, and HMI design for complex systems. So complex systems would mean defense, aerospace, transportation, maintenance, right? And I specifically look at the human experiential aspects of socio-technical systems. So when humans are there in socio-technical systems, how do you design for their experience? And three areas is, one is HMI design, human factors, and human systems integration. So all of these three come together when I'm thinking about any kind of HMI design. right? So I rely a lot on human factors as well as get a lot of ideas from systems engineering. The reason why we have to do this is because complex systems, right, are slightly different from your everyday non-complex systems, everyday normal systems. Part of the reason, and these complex systems could be something like a power plant, or a soldier fighting in a battlefield or a war control room. All of these aspects have a different dimension to it. So here, if you see in this picture, this is the point number 3, is where we actually do any kind of human technology interaction. Number 1 is or number 2 over here is the human and the immediate operational environment, how they both come together. And the third one is uh, hello, can you all see my screen? Is that
Yeah. Yeah.
Yes.
Yeah.
okay? I'm sharing, right? Or okay, I'm screen sharing. Okay, sorry, it had just vanished off. I'm so sorry. Okay, so what typically happens is that at any instance of interactions between complex systems, people are there in their immediate operational environment. But human performance over here also depends a lot on team based interaction. It also depends a lot on organizational based constraints acting on the behavior of the person. There in the background, government regulatory constraints. Then there are long range interactions and correlations which are affecting broader environmental pressures and market pressures and public pressures, right? All of this affect this bubble over here that we are designing for. So ultimately, even though we at the immediate level we are designing for this person over here, we have to consider this broader complex socio-technical system when we are thinking about design over here. This is a crucial demarcator of complex systems that is not found in your typical UI UX. So the work that I do falls under the area of OI and OX, operator interfaces, operator experience. And my research question typically is, how do we incorporate a human-centered design approach in these complex socio-technical systems? Now, this work that I do comes from human factors engineering, and the areas that we look at is called work analysis. How do we understand how people work? What are the different work environments in which they do their daily activities? And ecological interface design, which looks at this basic principle of designing for these constraints. So the work that I present has a lineage coming from the RISO laboratories in Denmark since the 1960s. So RISO laboratories was set up to look at nuclear power at that time. Now they have changed their focus towards green energy. And the work was done in the process control group with Jens Rasmussen and colleagues, who were looking at the display and interface design of experimental nuclear power plants. So the ideas started to come out of this group since the 1960s, later became more generalized, and later after 1990s, it became much more widespread, much more wide open, with the emphasis on ecological interface design. And today it's being used in a lot of different complex sectors, right? So the key ideas of these complex sectors include things such as supporting human variability in behavior, understanding the constraints qualitatively, and looking at it very much a formative and a synthetic approach towards design. So what does qualitative modeling of constraints is? What does it mean to have a constraint on human activity, and what does it mean to support variability? So for example, here I'm trying to hold my nose, but I cannot hold my nose because of these anatomical constraints. Now, typically, when we think about design for behavior in engineering systems, most of the time we have a normative approach towards design, which means the engineer will tell you, hold the nose like this. If you don't hold the nose like this, then there is an error, right? But human behavior allows you to have different areas where you are flexible. Human beings are variable. So what we basically need is a design process which takes into account the variability, but at the same time respects the engineering constraints of the problem. Right? We don't want systems to fail, but at the same time we don't want brittle systems where humans feel very cloistered. Right? So this is the basic idea behind the theory behind it. Some of the work comes out from ecological psychology, which is used as a basis for ecological interface design and systems design in itself. So here's what it means to sorry. Here's what it means to capture constraints for systems, right? Capture that when there is this is a very famous example of the ant walking on a beach from Herbert Simon. So there's an ant, it walks on the beach. Now there are two ways of thinking about the problem. One way of thinking about the problem is from the outside. You look at the ant, you understand the trajectory, you understand that the ant is an intelligent creature, and then you go ahead and model the entire system. Typically prominent in AI approaches, prominent in computer science. A different way of looking at the problem, same problem, is you try to understand what constraints the ant faces on the beach. The beach has sand dunes and other things, and it walks through the sand dunes. So if you understand the sand dunes, the behavior of the ant becomes very intelligible, right? So the idea is that you are asking what is it that the person requires to conduct certain activity in the operational environment. So human behavior then is a relationship between the person and the environment. And the key is, ask not what's inside your head, but what your head is inside of. Right? Understand the ecology in which the activity is being done. So that gives you a very strong foundation for supporting the experiential aspects of systems design, of the humans in systems, right? So another way of looking at this problem is through this way. So here you have to design for an operator. Now the operator, so you've got to design the information system. So this, as you would notice, is the inner bubble number 3 of the previous slide that I showed you. This information is the designer's problem. You've got to design an information system over here. The operator works in an operational context and has mental models about that operational context. Now the designer has two ways to think about the problem. One is from the experiential viewpoint, typically prominent in all these fields of user experience, human-centered design, interaction design, right? Where you look at the entire operational context from the viewpoint of the operator, from the viewpoint of the end user or the human, right? And then there is another way of looking at the problem, and that is the engineering way of looking at the problem. That is, you are taking this entire entity and you are recognizing that the human is a system component, right? And you've got to optimize this entire system. So the human is a system component, the system is the human's environment, and both have to be optimized together. So when we think about operator experience and operator interfaces, both these viewpoints have to be taken together, one as well as two, which means it is not that we do not recognize the engineering dimensions of the system, but we have to ensure that the experiential dimension is not reduced to the engineering aspect of it. So both have to be balanced together, right? And we have to understand how to support the operators informationally as well as experientially, right? And we have to understand the deep structure of the activity in context while recognizing the constraints of human performance. So some of the work that we do is looking at work analysis techniques, also called closely related to the task analysis techniques. Work analysis and task analysis, activity analysis have differentiations, slight differentiations in the way they look at it. So we do a work analysis approach. We start with activity in operational context. We start from step 1 and move towards step 5 to worker competency analysis. And based on this, we look at the environment, activities, and the person, right? So we ask, what is it that is required from all these three entities to do good HMI design, right? Once we get the requirements, this leads us, so we do operator studies. So we spend a lot of time with operators in the field. We try to understand how is it that operators work in power plant control rooms, how is it that maintainers go ahead and do maintenance, right? And then we go ahead and use work analysis techniques to model them. Then we look at the design requirements. Based on this, one direction is interface design, the other direction is you can train the operator also. I personally look at more interface design aspects. And here are a few examples that I've done. One is HMI design for a digital twin of a CNC machine and a lathe machine, and we did a whole user interface for them. Notice that what we are trying to do here is capture the logic of how people are thinking about it. So this point is the point where your tool connects to the job and where it's cutting it, right? So this is your feed rate and this is your spindle rotation. Now, once this friction is happening, heat is being generated. That means your job temperature keeps on going up. Now you have coolant pouring on your tool and the job to keep the temperature down. Otherwise, that will melt and stick to the tool over there. So what we are trying to do over here is visually trying to show that, notice that if you increase the feed rate, and if you increase the spindle rotation, it may go into these areas. It also may go into these areas, right? And in this area, your tool will break. So visually, what you are doing is you are ensuring that the constraints of activity in the real world is acting back, right? It is acting back. And this constraint needs to be shown to the operator so that based on this, they can then go ahead and make decisions, right? So here, if the spindle rotation is increased, your job temperature increases. Now, let's say if you had less coolant, right? Which means this red region would have come to this region, right? So in that case, what you would have done is decrease the spindle rotation, right? So in these ways, what we are trying to show is that there is not only one way but different ways possible for the operator to act, and all of these ways need to be supported or at least shown in some way or the other. So this is one example. This is another example that we did for the for a health and usage monitoring of the rotor wing of a helicopter. And here what we are looking at, things like, here is the entire session. At this particular point, there are certain problems that are going on, right? So how is the temperature, RPM and vibration connected? Here you'll notice is that there is a region, we don't know what the problem is, but we do know that there is some problem, right? And because there is some problem over here, then the operator, the maintainer is alerted to the fact that there may be something going on. Now here we know for certain that one sensor has failed. And because one sensor has failed, then what is going on is that here we can show for certain that this is a problem. So in these ways, what we are doing is that we are supporting. Here's another example, another view of the same HMI. Here we are visually showing that, okay, this may be the problem exactly because we have found certain faults over there, right? This is another example of an HMI for smart maintenance in the trucking industry. We asked the question, how is it that digitalization is changing the trucking industry in India? And in India, what the interesting thing is that truck owners, there are a large number of truck owners who have less than 5 trucks. So this is the industry wide setup, north as well as southern parts of India. And this study was done in trucking of trucking in Salem, Tamil Nadu, which is in the southern part of India. And currently, engines have a lot of sensors to identify the health, right? Now, the big challenge is that in the future, with the coming in of IoT, many parts of the truck will have sensors. They will give a lot of data, right? How can we help truck owners by identifying the health of the parts to support predictive maintenance or health monitoring of these trucks, right? So these two are in Tamil. I'll show you some examples. And we are dealing with very low literate users over here, low literate, but they can use mobile phones, and they do a lot of those activities on the mobile phones. So how do we use the mobile phones for low literate users, but at the same time enable them to get their work in process, right? So an example is that given the current state of my truck, of this truck, if I look at the recommended service, it will cost me 9,000 rupees and 3 days downtime. Now, can I afford this amount, and can I afford 3 days downtime? If I cannot afford it, given the current state of the truck, I can travel in this bubble. I am over here. I can travel either to here, either to here, or this over here, right? So this helps the truck owner to recognize that, okay, if I have less money, then I can go ahead and actually do all my activities within this region, and then I can drive back and then take the money and get my truck repaired. So this research recently got covered by Nature India podcast, in how the mobile industry is really changing Indian landscape. And this brings me to almost to the end of my talk. I look at human centered design, a lot of systems engineering and human factors, and HMI design, human factors, and human systems integration all have to be taken together. Some of the work that I had presented, few of my examples were mostly for engineering systems or complex systems, and how we can go ahead and help the users, end users, or in most cases operators, OI, OX, to go ahead and make sense of a lot of their work that they're doing. And that's all from my end. Now I will stop sharing.
Thank you, Vivek, for a very informative overview of your work and your interests, and for this area itself. I'll just start off with one very quick question, knowing the audience we have today. What do you think are the major obstacles that researchers and people working in the area of HMI have when conveying the needs of users to systems designers and engineers? So we're coming from two different domains, and how do you bridge that, basically?
Yeah. So one of the things which I learned over the period of my education was, so I started off in electrical engineering. I got interested in UI UX, and then I studied cognitive science, and I studied psychology, and then I did a PhD in system design engineering with HMI focus. Right. So I completely understand. See, what happens is that most of the time these ideas are supposed to be commonsensical, and this is one of the biggest challenges I find, convincing engineers that the end user really may be thinking differently from what you're thinking. And it is not enough to simply ask the end user for your solution, because your end user is not your designer. So there's a user, there's a developer, and there's a designer. So in India, what I've been finding is that bringing in the view of the designer, especially in these traditionally heavy engineering sectors, which are dominated by engineers, is a big challenge. We require, a lot of my research involves creating user centered techniques, human centered design techniques, work analysis techniques, which will help you to really try to grasp what are the scenarios, what specific variables you need for a particular time. So most of our challenges then happens is, one, how do I go ahead and create these processes which actually help the engineers, rather than telling them we are right and you are wrong, because that doesn't get anyone anywhere. But how can we get together and really think about the problem from a psychological dimension, from a design dimension, as well as an engineering dimension, and club them together. So that, I think, is one of the biggest challenges.
No, I think that's great, and I love your approach of thinking of the user as a component in the complex system, not external to the complex system. And I think, factoring that from the outset makes for a better design and a better usable system, etc. I'll throw it out to the floor if anyone else has any questions. Okay, maybe in the interest of time, because I want to be respectful of everyone's time, I'll hand back to Fabrizio. And thanks again to Vivek for a very, very informative talk and for representing the HMI.
Let me join David in thanking you, Vivek. It's very, I think, a hot topic, not just as you said for the, those working in this specific area, but it's really at the intersection of many of our technical committees. So thank you for this inspiring and relevant talk. I just showing for a second again our slide just to introduce the second speaker and thank the second speaker, Professor Alex P. James. I'm not sure there are the officers of the QCT Technical Committee. If not, maybe I can hand the floor to Davide for introducing Professor James, if you are available. Davide?
Yes, thank you. So Alex is not from our CTSoc. And I don't know him very well, but he's a professor and dean of the Digital University of Kerala. And he will talk, the title of his talk will be his Emerging Memories for Analog Computing. And I will leave the floor to Alex. So.
Yeah, thank you. Mine is less of human and more of machine. So I'll try to make
We need
it
them. We need them too.
Yeah. So let me just share the screen.
Thank you, Alex. I know him, by the way, because he is, of course, one of the officers, by the way, of the MDA on machine and deep learning in consumer electronics. By the way, he's working at intersection in the computers, as you said, and VLSI and CAD domain. So today the talk is an intersection of these areas. Please. Alex, when loading is completed, I think.
Is it visible?
We see loading only for the moment.
So it's on my side, I can see that.
Maybe you can stop sharing and share again.
Okay, let me try once more.
Because it's not updated, maybe. No, it appears for a second white and green, and then now I see just the loading. Not sure. I don't know if it is the shared docs or it appears just for 1 second and then it disappears. We see the browser. Okay, now it's okay. Probably when you go, okay, because you share it probably not the full screen, but the application. So when you go full screen, we see it black.
Okay, let me.
So either you share everything or we stay like that.
I shared the full screen.
Now, okay. And now if you go like this, yes, it's working now.
Okay, perfect.
Thank you so much.
What I'll quickly do is I'll run through some of the basic concept, like what this area is about. And what you can do with emerging memories in building like various systems around like analog compute. So why analog? So if you look at the entire like system of devices that we have today, you can see there's lots and lot of sensors that's going at the edge. And increasingly more with IoT and all sort of different communication protocols, we add more at the edge. And when you have like much more happening at the edge, rather than sending the data to the cloud, the idea would be to do the processing next to the sensors. And when you think about that, a lot of data that we get from the sensors, they are of analog nature. And then the obvious question comes in, why not then do those computation in analog domain itself rather than doing it in digital? So that's exactly what a lot of use of analog compute goes into. Overall in this research, this makes a lot of sense to do it because you can do compute at extremely low power, low energy. Those decisions that come out of those edge devices only need to be transmitted to the cloud, thereby saving communication bandwidth in many of the applications. So that's primarily the application level reasoning of why one need to think about like analog compute. And part of the analog compute is also how do we implement various like statistical methods or even various deep learning neural models, which are very useful these days to process the data from the sensors in real time or otherwise. And if you look at the number of AI studies, and there is a strong correlation between the technologies, the semiconductor technologies that we have and the evolution of it. So as and when the technology scaling happen, better, more compact like processing systems start to come into being. And you could see it really helped with building deep learning, large neural networks at scale. So, which also means then we could do a lot of things with data, which otherwise was not possible in the previous technologies. And that's a very good reason why we need to build new kind of devices as well as like new hardware-based AI systems so that you can push even more into that area. Overall, if you look at the landscape of the technologies, you would see to a large extent GPU-centric computing is what we use today. And the training aspect of is you could see that practically most of the training with GPUs hardly happen because it's not energy efficient. And ASIC-centric computing also the same. And that's where analog-based computing and neuromorphic computing, all those unconventional computing comes into picture where you try to cover all the various different boxes of inference and training, both for cloud as well as edge. Increasingly, three things are affecting the hardware: Moore's law, memory wall, and heat wall. And alternative to that, definitely neuromorphic computing, analog computing comes into play as a major technological ideas. Now, these are some of the emerging memories. Typical memory technology, you can see SRAM, DRAM, and flash. And over the years, the scalability of SRAMs has been pretty good. But flash has certain limits. And because of those, people started to look into other kind of memories to reduce the size as well as to have better scalability. And many different types of resistive memories have been proposed, both at an industrial scale as well as at lab scale. And some of these are already silicon proven, and many are in the line. So you can see these technologies, they also vary in terms of the read time, write speeds, the endurance, and so on and so forth. And in terms of scalability, some of the memories are emerging memories are already like achieving what a SRAM could do. So another aspect of these technologies is that because many of these are resistive-based memories, you can also program these resistant state And when you program these resistant state, you're no longer thinking about just binary storage, you're also thinking about like analog storage. And the beauty of that is you can try to now think of systems which can really do like analog level compute on the memory. So that's where the whole idea of like memristors and neural compute becomes like quite interesting. All class of these devices, we can call them to be at a higher level as memristors. And what it essentially does is it comes out of the theory proposed by Leon Chua in late 60s and early 70s of a two-terminal device which could relate flux, linkage flux with charge. And if you see the voltage versus current plot, you could see here that hysteresis properties, like pinched hysteresis property, is something that you observe in almost all the memristor devices. And they can be bistable, they can be of volatile nature, they can be of non-volatile nature. And the entire like memristor behavior can be modeled as a two-state equation. And the dynamic behavior of these devices could be understood by having a phase plot, like dynamic route maps. From there, you can figure out like the switching behavior and whether it's a volatile or non-volatile device, and so on, hence and so on and so forth. Because these devices can be programmed to various resistance levels, you can have like ways in which like these devices can be used to store weights. So each of those analog weights in a neural network could be translated to conductive values of each of those memristors. And the way you can do that, you can, in fact, place the memristor devices along with a switch or a selector in a crossbar configuration. You can apply the inputs as voltages through the rows, and you can read the currents through the columns. And simply, if you look at here, each of these nodes with a memristor, that's like a conductance value. And the currents here will be simply a weighted summation of those conductance and the voltages, which is similar to how weighted summation or MAC, multiply and accumulation operation, happens in a single neuron. So in fact, if you look at the crossbar, each crossbar can be used to mimic a single layer of a neural network. And several of these crossbars collectively can be used to build neural networks. So if you could build these kind of modules, crossbar modules, then you can try to build all sort of different applications around it from various kinds of neural networks. You can create like generalized logic gates. We can create memories, NAND or associative LTM, and so on and so forth. We can use it for cryptographic applications to generate keys or to solve like factoring problems. Or because it's a weighted summation, you can use or rethink it as a set of linear equations and use it for solving PDE or as a linear equation solver. And you can also use it for certain applications like in image processing, where convolution operation again uses like a weighted summation. So all those possibilities exist with this kind of hardware. Now, what are the challenges that come with it? Many of these devices do have various stability as well as like variability issues. There could be endurance issues in the device. Whenever a new device is introduced, these devices would have like all sort of variabilities to be taken care of. How do we program this? Programmability challenges, whether it's like a linear programming, whether it's a nonlinear programming, the kind of peripheral circuits that you would need to ensure that the crossbar or the computation become accurate through variety of different like circuit configurations also becomes like a critical thing to work out. So these are some of the devices that were fabricated, and you can actually study the behavior of these devices, similar to how originally was proposed with like various state equations. And these devices could be then used for building like various kind of systems. For example, like if you want to have a single layer of neural network, you can have a weighted summation operation implemented as like a crossbar configuration followed by a softmax. Now, softmax also can be implemented as like a set of winner takes it all circuit and other to build the entire circuit schematic. Now, in terms of analyzing the capabilities of such networks, two-level things are looked at. One is performance, another is a generality. And we often compare it with the human level performance of the system. And entire landscape of the technologies of AI chips built with various like analog memory systems. If you look at from an accelerator perspective, you can have like digital only solutions where this can be integrated into an ASIC or a GPU, or as a mixed signal configuration where it's purely memory based or it's like a CMOS logic based. And for a more generalized purpose AI to be built, this may be still like at the early stage where we look at various different idea of like generative or bio-inspired models to be built around it. Now, why should we do that? The primary reason is that like energy consumption of many of these neural networks, when you make it large to implement in GPU and others, they are quite like energy hungry. It's not necessarily the chips itself, it's the peripherals and the other large set of like boards, memories, compute that is required. They make it like fairly energy inefficient. So one of the things to be looked at is how do we make these things more energy efficient. Now, one of the things that you really see is like the variability in these devices. And the question that we ask is like, is variability really bad? And can we actually make use of this variability to build things? And there are a variety of issues within the crossbar that you would see, like leakage currents or various kind of non-idealities. So with variations itself, can we still do reasonably good architectures? And you can see some of the results here, even with a large variation. If you train the system in a way that it can tolerate these changes in conductance, it still doesn't really affect the overall like recognition accuracy and things like that. Now, another thing that we looked at is we also looked at whether it is possible to really build like on-chip learning, and can we do that in analog compute and build like various blocks related to that with these crossbars. And this was one of the early works on backpropagation, how you can in fact like build the entire like feedback kind of networks, everything in analog, and you can place this close to the sensors. So which means you can in fact have online learning next to the sensors without sending it to like complex compute. And likewise, we can think about like various different kind of neural networks to be built. And that's what we have been exploring. Can we do HTM circuits, for example, which has temporal polar and spatial polar, and can we build all these configurations and find certain applications like in face recognition? Can we do like a single chip based like face recognition where the compute can happen next to the pixel itself rather than having like an A to D converters and sending the data, and we do it just next to the pixel. Another thing is we also did like some comparison on HTM and CNN to see the generality and how the systems work. HTM like networks are fairly generalized, but they are relatively harder to train. Whereas like CNN, LSTM kind of networks, which are like planar, they can be much more easier to train with backpropagation. We can also improve the energy efficiency by adding like dropouts, and this dropouts we try to do this both at like inference as well as like at training stage, and a significant improvement in energy efficiency was achieved. But obviously, when you try to do this at inference stage, the accuracy will slightly drop. So it's a question of how much you want to save. Whether are you okay with like reducing the accuracy a little bit, but you save like significant on the energy. So from a hardware perspective, in many of these applications which are close to the sensor, you want to save the battery power. So it would make a lot of sense to have like these kind of like dropout networks to go in. So these were some of the results like that we found that like even with like variability and even with like various kind of adversarial attacks onto the sensors and onto these networks, it would still give like fairly decent performance. Just skip some of these. Another technique that we recently developed, like is to basically to come up with a very simple technique by which you could kind of get around the problem of variability affecting the overall performance. So all we did was we just connected the rows of the crossbar. But when you do that, it starts to show very interesting properties. And we came up with like few theorems, and it can completely predict the conductive behavior. So having like few levels, conductance levels, you can connect these memristors in parallel to actually achieve like a very high number of stable conductance level. Now, what it means is that you can do analog compute with high resolution by doing this without, in fact, having to worry about increasing the individual resolution of the devices, individual devices. And that solves one of the major problems that one would have building like a crossbar and devices which are unstable. And with CNN architecture, we tried to prove this with a complete like analog implementation of such a network, that you're having like even few number of resistive memory devices, you can in fact like have high accuracy as good as like the algorithmic level accuracy that can be achieved in ideal conditions, even under variability. And further to this, rather than just parallel, then we started thinking about, is there a better or even more ways to program it, and is there any other techniques in which like we could. So we started exploring bridge configurations and few others, and we found that it's not just like one particular way in which you can build those super resolution and stable conductance level. You can also build it with variety of other configuration. Although the math or deterministic like approach of getting exact number of levels is much more simpler when you connect in parallel. With bridge, you can achieve these at much more higher resolution as well. So if there are certain applications where you need much more number of like stable levels, then this kind of configuration with programming the states one would be able to achieve. And these are some of the results that we could see, that you can see here. While the parallel would achieve like 4,000 equivalently with equal distribution of weights, a bridge configuration would achieve like 36,000. This way, one could achieve much larger number of like stable conductance level than one could achieve it parallel. But still, compared to a single device, even parallel would serve as a good simple solution. If you have already like a fabricated crossbar and you don't want to change that configuration, then going through a parallel implementation becomes much more useful. These are some of the results. Another challenge that we have is often designing these networks. So what we did was we found some of the ways in which you can optimize the design using genetic search and others, bring up recommendations for various like hardware units that needs to go into making the neural networks. So rather than manually building these analog like networks, this approach we take like into account various hardware performances as well into account while designing the network itself. So that way, the effects of variability, effects of aging, and all those things get are considered while the design itself is done, rather than you design it first and then try to figure out how to optimize. So this way, you save a lot of time in making the overall design of the circuits. This is some of the results. I'll skip. So main challenges going ahead, we see that reliability and reconfigurability of chip as we further integrate like larger number of devices. So when you go from say hundreds and thousands of devices to millions, the complexity increases further. And as and when we do that, we need to look at like how do we pack more in a single chip. So 3D integration challenges of chiplets and all these kind of system becomes like kind of quite a bit of challenge to look at. Energy area, speed efficiency, all of these are still some of the challenges as we go further. Biocompatibility and multi-sensor integration issues are something that we increasingly see as important if you want to integrate that into sensors. And many of these sensors might go into for bio applications, on-body sensing, and many others. So we have to be mindful of those constraints that are going to be there in terms of EMI, EMC, and the way you build the chips. All these processing to be done next to the sensor, it has to be something that is compatible with all those standards. And we also are looking at like, can we think about like, because there are a lot of generative AI and other aspects being looked today, what are the kind of hardware that is required to build those? So, and from the design point of view, we already started like using things like generative AI for like building some of these blocks within the chips. Verification is another, multi-objective optimization, especially considering both the system level challenges or like performance in terms of hardware, everything to be taken into the objective function rather than just looking at like accuracy or say F-score or things like this, which would only look at the neural network performance. So along with those performance metrics, one needs to also consider all sort of other hardware chip related issues part of like developing those networks. Neural search, automated neural search is another major problem at hand, because there are so many different ways in which you can connect and find what are the right set of architecture. So searching the kind of right kind of architecture becomes also a problem when you are building like dedicated ASICs and chips around this. Training is also, on-chip training is an open-ended problem that many of us are working in this area. Now, if you look at like the barriers of these power distribution within those chip becomes more and more complex. As and when you have more devices going in, the number of interconnects, number of lines that go into the chip, the physical design of the chip itself, especially with analog, becomes a bit of a challenge. And one needs to carefully consider all those data path issues, the power distribution issues, the interface logic. Device reliability itself is being addressed in many different ways. For example, the previously something like a super resolution crossbar can help overcome many of those things. But when it comes to peripherals, the compensation that needs to go into those chips, they are all still like quite a bit of like interesting problems to work with. So in summary, these are some of the things that we need to think about in this area. One being like not just implementing the neural networks from an algorithmic perspective, but also think about building the right kind of chips for the right kind of algorithms. So a hardware software co-design approach is something that one needs to look at in an analog compute. What should be coming first? Should you build the hardware first or should you build the algorithm? That's a question always, and a large set of answers come by looking at the application itself, and then try to work around a solution. Now, would we really go for a online or offline learning? And these kind of things again is very much depending on what you really want to do in terms of like that application. So in some case, if you want to build that analog compute within the server, then you are looking at probably the constraint of memory is much less there. Whereas like if you are looking at an edge application, the memory constraints and compute constraints becomes much more heavier. So the kind of solution or the learning mechanism that you need to adopt also is like very different. And systems thinking is something that is very, very important when it comes to building larger systems. So although we are talking a lot of circuits and related aspect to select the right kind of circuits for the right kind of system, that systems thinking approach largely would help in building those practical applications. So that's primarily it. Thank you.
Thank you, Alex. I'm wondering if there is any question for Alex. I think we have, for the sake of time, just maybe one question because we're a little bit late.
I have a small question.
Thank you, Davide.
And thank you for the speech, Alex. It's very interesting. But I wonder how far we are from seeing these kind of emerging memory technologies from become as consumer as other conventional computation like GPU or CPU.
So many of these things. So when we are looking at like memories and thinking about it as conductance devices, already flash memory could do that. So you can have DRAMs. You can also use SRAMs for building such arrays. So in terms of building practical systems, that is already possible with these. But when we are talking about some of the PCM or RERAMs, there are few foundries which already support it. And some of the exploratory chips have been there in the last few years. Like, for example, from an industry perspective, if you look at IBM had come up with an analog resistive like array and a chip. There have been few universities, including us, like now we are building like some of those. And they are all going into practical devices or practical consumer solutions. Now the challenge is like reliability and all those things. Whenever a new memory comes in, you need to go through all sort of like real testing to make sure that that is adopted at scale. Cost is another factor. Is it going to be competitive in terms of cost? Now, the good thing with many of these analog compute is you can avoid a lot of circuit which you typically would need with a traditional DRAM and SRAM. The peripherals can be simplified, like because the weighted sum or the MAC itself is done in analog. You don't have the overhead area that comes with digital multiplier implementations and other things. So even in-memory processing can be simplified for the compute part. So there are many good advantages that you would see. And if we can integrate like the blocks to the sensors, that's what many people are trying to do now, then you save a lot on having like an additional chip, and you can simply have like chiplets and others to configurations to have like sensors and this integrated together. So it's happening, and it's getting to that level where it's going into products.
Thank you.
Great. Thanks also for the question. Let me thanks again all of you for attending, and of course our speakers, Professor Kante Vivek and Professor James. Alex, thanks a lot. I think that this kind of activities are creating a common ground that is stimulating the discussion among our different TCs and in CTSoc as a society. So thanks again. The next webinar is planned to be held in March. Probably we might have more speakers and a webinar not every month, but every 2 months. But anyway, you will receive news about that through our channel. So thanks again. And thanks also to David and Davide for helping me to chair. And see you next time. Bye-bye.
Thank you. Bye.
Bye-bye, everyone. Take care. Bye-bye.